Assalamualaikum students, welcome to Electronics. I'm Madam Rosmina Zwin Abdurrahim. Okay, as usual, let's start with a hadith. It was reported by Malik ibn Anas, may Allah have mercy on him, said, "Verily, it is the duty of a student of knowledge to behave with dignity, tranquility and reverence, and to follow the way of those who came before him." Okay, so being a student of knowledge, good manners should always come together. Okay, so we should always portray good adab, good akhlaq when interacting with others, and take our Prophet Sallallahu Alaihi Wasallam and the Sahabas as the examples in our life. Now let's move to chapter 2, Semiconductor Materials and Diodes. This video is on chapter 2b, which covers two subtopics. The first one is on currents in semiconductor and the second one is on PN junction. For the first subtopic, currents in semiconductor, there are a few concepts that you have to know. First, about the current, where current actually is generated by the movement of charge carriers, meaning when the carriers are moving, there will be current. Okay, but what are the carriers? Carriers actually refers to electrons and holes in the semiconductor, and this carriers movement which cause the current to flow are due to two basic processes, which are the drift, which is caused by the electric field, as well as due to the diffusion, which is caused by variations in the concentration. Okay, now let's have a look on the drift current concept for N-type semiconductor. So as we know, for N-type, the majority carriers are electrons. Okay, so when we apply electric field, for example, in this direction, we are going to get the flow of electrons, okay, in the opposite direction to the electric field. Why? Because electrons, they are negatively charged. Electrons, they are negatively charged. So because of that, they are going to move in the opposite direction to electric field. Okay, then another thing that you need to know, once electrons are moving, they acquire a drift velocity, which is actually given by this formula. VDN equals minus mu n times E. Okay, minus refers to the opposite direction of the flow of electrons. So mu n actually is the electron mobility and E is the magnitude of electric field. Okay, then the electron drift actually produce a drift current density, which is given by Jn equals negative En VDN. VDN is the velocity just now, and En actually, E refers to the magnitude of electronic charge and N refers to the electron concentration. Okay, meaning to say higher current density we are going to get if electron concentration is higher, or if higher electric field is being applied to our N-type semiconductor. The same drift current concept actually can be applied to P-type semiconductor. So as we know, for P-type semiconductor, the majority carriers are holes. Okay, so when we apply electric field, for example in this direction, we are going to get holes which are moving in the same direction with the electric field. Why? Because holes, they are positively charged. Okay, then once they are moving, actually they acquire the drift velocity, similar formula like in the N-type. Okay, in this case VdP equals positive mu P times E. Why positive? Because it's moving in the same direction as E. Then later from there we can get the current density, which is given by Jp equals EP times VdP. Okay, the same thing. E actually is the magnitude of electronic charge, P is the hole concentration times the drift velocity of these holes. Okay, from there we can get the current density in P-type semiconductor. Okay, since in semiconductor it contains both electrons and holes, right? It contains both electrons and holes, so we need to consider the total current density for both electron and hole components. Okay, meaning the current density for electron just now is given by this formula, and the current density for the holes are given by this formula. So the total current density is the sum of this current density for both carriers. Okay, which is actually equals to the conductivity times the E, which is the magnitude of electric field. Okay, then the conductivity is actually given by this formula, En mu n plus Ep mu p. Okay, so in overall, this is the drift current formula for both electrons and holes. Then talking about diffusion current in semiconductor, actually as I mentioned before this, it is due to the particles movement or particles flow, okay, which are holes or electrons from the higher concentration to a lower concentration. Okay, so because of this concentration gradient, it will cause flow of electrons or holes, and obviously it will cause diffusion current to occur in our semiconductor. Now we come to the second subtopic, which is on PN junction. Okay, so PN junction, as the name it is actually a combination of P-type and N-type of semiconductors, okay, where we combine it together so to form a PN junction. But just a little bit of revision, as you know, for N-type semiconductor, the electrons, they are the majority carriers, right? N-type, negative type, the electrons are the majority carriers, then obviously the holes are the minority carriers. So as you can see in this structure, we are having both majority and minority carriers, but at the same time, you are having donor ions. Remember the impurity atoms, okay, that we dope into this N-type, okay, so these impurity atoms, they are willing to donate electrons, right? So they become donor ions, and these donor ions, since it gives away electron, it donates electron, they are positively charged. Is called the positive ions. Okay, then coming to P-type is about the opposite from the N-type, where the holes are the majority carriers and obviously electrons are the minority carriers. So as we can see in the structure here, we have both holes as the majority and electrons as the minority, and the same thing goes to the ions, where we have the acceptor ions who are willing, remember group 3, they are willing to accept electrons. When they accept electrons, they become ions, then obviously negative ions. Okay, one thing that you should take note, the carriers, the electrons and holes, they are moving, they can move in the semiconductor structure, but ions, they are going to stay, they are not moving. The only things that are moving in the structure are the carriers, holes and electrons. Now let's see what happens if we form a PN junction together. Okay, we have P-type, we have N-type, then we connect them together, okay, through fabrication process. So once we have this PN junction, what will happen? First, obviously, we join both N-type and P-type together to form a PN junction, right? Then what will happen next? Actually, remember the majority carriers for this N-type are electrons, and the majority carriers for this side, for P-type, are the holes. So what will happen? Electrons will tend to diffuse from N-type to P-type. Remember, higher concentration to lower concentration, because electrons, when they are at the N-type side, they are the majority carriers, okay, but when they come to P-type side here, they becomes the minority carriers, meaning at this side they are having higher concentration as compared to P-type. Okay, so that's why electrons, they tend to diffuse from N-type to P-type. And in opposite, obviously, holes tend to diffuse from P-type to N-type, again because of the concentration gradient, right? So we have the diffusion of electrons and holes, okay, then because of this, at the junction, these electrons and holes, they are going to combine and become neutral. They are going to combine and become neutral. So once they become neutral, remember I was saying just now, the carriers are moving in the structure but not the ions. Okay, so at the junction, since electrons and hole, they combine with each other, becomes neutral, so the only ions that will remain at the junction are the positive ions as well as the negative ions. Okay, so positive ions coming from N-type side, negative ions coming from P-type side. Okay, so once we are having positive charge, positive ions, and negative charge coming from negative ions, actually we are creating a charge separation that somehow sets up electric field. So in this case, electric field will be created from positive to negative. Remember, at this time it is at equilibrium, meaning we are not connecting this PN junction to anything. Okay, so what will happen? Electric field will be created. So once electric field is created, there will be a kind of force that will somehow stop the diffusion of carriers. Remember, in the beginning, electrons and holes are starting to diffuse, right, because of concentration gradient. But once electric field is created, it will somehow stop this diffusion. At this time, we say that this PN junction, it reached its thermal equilibrium condition. Okay, so there will be electric field, there will be no more diffusion of electron and holes. The only ions that are there at the junction are the positive ions and negative ions, and this junction, this region, okay, we call it as depletion region or space charge region. Now let's have a look on the energy band diagram for PN junction. So if you recall, in previous video I mentioned about energy band diagram for each N-type semiconductor as well as for P-type. As you can see here, the Fermi level for N-type is towards to the conduction band, while the Fermi level for P-type is more towards the valence band. So when we combine these two materials together, okay, then we align the Fermi level. As you can see here, the energy band for the for the N-type side is much lower compared to P-type material. Okay, in that case, electrons from conduction band need some kind of energy, some amount of energy for them to jump from conduction band at N-type to the conduction band at P-type. Okay, so this amount of energy is called as built-in potential, meaning to say, for the electrons or holes to be able to cross the junction. What is the junction? To cross the depletion region, it needs for some amount of energy, which is called as built-in potential, built-in voltage, referred as VBI here. The VBI that I mentioned just now actually can be calculated using this formula, where VBI is given as KT over E ln NA/ND over Ni squared. VBI equals KT over E ln NA/ND over Ni squared. All the coefficients and parameters are given here. Okay, what I want to highlight here is KT over E is actually, we call this as thermal voltage. If it is at room temperature, then it's always to be equal to 0.026 volt at temperature of 300 Kelvin at room temperature. Okay, so meaning to say, if we calculate the VBI value at certain amount, it shows us how much potential is required for the carriers to be able to cross the junction, to be able to cross the depletion region, to be able to contribute to current flow. As you can see from this example, using the formula, we can actually calculate for the VBI value. So if we substitute all the values given, okay, this is at T equal 300 K at room temperature. So VT, straight away we can put 0.026. Or else, if T is at different value, you have to calculate KT over E. Okay, then ln NA/ND over Ni squared. If you substitute everything, you're going to get this value is 0.757 volt. What does it mean? It means that we need a voltage about 0.757 volt for the electrons and holes to be able to cross the junction, for the carriers to be able to cross the depletion region, for them to contribute to current flow in this PN junction. Here is another example, but I reserve it for you to do your own self-revision. If you calculate this, okay, you are going to get these answers where at the end, you are going to get VBI equals to 0.922 volt. Okay, but take note, for this particular example, the temperature is not at room temperature, meaning you have to calculate the VT first, where VT equals to KT over E. Okay, so calculate this first, then you need to calculate for Ni, then only you substitute everything so that you can get VBI equals 0.922 volt for this example. What does it mean? It means that the carriers need for at least 0.922 volt for them to be able to cross the depletion region. Okay, now we come to reverse bias PN junction. Okay, the one that we discussed before is at thermal equilibrium. Okay, now we put the PN junction under reverse bias condition. So under reverse bias, it means that this P type is connected to negative terminal, okay, of the voltage, and this N type, which is the negative type, is connected to positive terminal, positive polarity of the applied voltage. Okay, so by having this connection, you are making this PN junction to be under reverse bias. Okay, so what will happen under reverse bias? So as you know, initially at thermal equilibrium, we already have one electric field. Remember, electric field is kind of force that stop the diffusion at the depletion region. Remember? Okay, now when we apply another applied voltage here, actually we are introducing another electric field to this PN junction. Okay, then obviously this electric field direction is from positive to negative. Okay, so here in this case it is labeled as EA. Okay, so as you can see here, we have additional electric field on top of the existing electric field from thermal equilibrium, meaning the total electric field will becomes higher. Okay, it gives higher magnitude of electric field. Okay, so this increased electric field is kind of a force, introduce additional force to our holes and electrons, so to stay away from the region, I mean not to cross the region, because remember the electric field, they act as a force to stop the diffusion. Okay, so meaning to say more force will be there now at the depletion regions, and obviously the depletion regions width becomes wider. Why becomes wider? Because electric field now is increased. So as you can see from here, the width of depletion region becomes wider. Why? Because we have increased electric field. Why increase electric field? Because another electric field is coming from the reverse bias connection before this. Remember? Okay, so this electric field, they act like a force to the depletion region, which will stop diffusion of carriers. Okay, then obviously it will push away all the carriers from the depletion region, so that's why the depletion region width becomes wider. Okay, so in this case no current will be going across the junction, because since depletion region's width becomes wider, obviously we need much more voltage to be applied in order for the carriers to be able to cross the junction, right? But by right, in reverse bias, it's difficult for the carrier to cross the junction. Because of that, no current flow will be there. Okay, then with the increase of electric field, obviously there will be an increase in terms of charges. Remember the positive ions and negative ions. Okay, so this increase of charges actually can be calculated in the forms of capacitance value. So that's why in reverse bias condition, we can somehow calculate for this capacitance value at the junction, which is called as junction capacitance, and this is given by this formula: Cj equals Cj naught times 1 plus VR over VBA power of negative half, 1 over 2. Alright, okay, so under reverse bias condition, we can actually calculate for the charges value in terms of capacitance, okay, using the formula given. Okay, for this example, as you can see here, the junction capacitance actually is also related to the VR as well as the VB. VB is actually the VBI, the built-in voltage that we calculated before. Okay, so once we know the VBI value, and if it is given the reverse bias voltage is 3.5 volt in this particular example, we can substitute, then we can get actually the junction capacitance value, in this case 0.59 picofarad. Now we come to another configuration of PN junction, which is called the forward bias. Okay, so in opposite to the reverse bias, forward bias, in this forward bias, the connection of our PN junction is like this: P type. P type is the positive type, right? It is connected to positive polarity of the applied voltage, and N type, which is the negative type of semiconductor, is connected to negative polarity of the applied voltage. By having this connection, we are saying our PN junction is under forward bias. Okay, so the same thing happens where initially we already have one electric field due to thermal equilibrium, remember? Okay, once we apply another voltage here to our PN junction, we are introducing another electric field. But in this case, the electric field will be in the opposite direction with the existing electric field, the thermal equilibrium electric field. Okay, so because of that, the total magnitude of electric field will be reduced because these two electric fields, they are in opposite direction, remember? Okay, so when the electric field is reduced, the force also is reduced. Okay, then what will happen? It will somehow cause the width of depletion region also becomes reduced. Okay, so in this case, the diffusion process, remember, electric field is kind of a force to stop the diffusion process. Now since electric field becomes reduced, the diffusion process may occur, okay, as long as we apply the voltage here. Then since diffusion happens, there will be movement of carriers, movement of electrons and holes across the depletion region. Obviously there will be current in our PN junction. Here is the same thing that I mentioned just now. Under forward bias condition, what will happen? The width of depletion region becomes narrower due to reduced electric field. Why reduced electric field? Because we are having two electric fields in opposite direction. Okay, so since the width of depletion region becomes narrower, so obviously it will be much easier for the carriers to cross the junction, to cross the depletion region. So it will cause diffusion of carriers. So obviously it will cause current to flow across the region. Okay, from there we can actually get the ideal current voltage relationship, which is given by this formula. Okay, where ID is the diode current. Okay, because remember, when we are talking about PN junction, we are actually talking about a diode, PN junction diode. Okay, so in this case, when there is current, this current is referred as ID, diode current, which is given by IS, which is the reverse bias saturation current, is very small, times exponential Vd over nVt minus 1. Okay, since Is value is very small, sometimes this formula can be approximately equal to Is exponential Vd over nVt. Let's have a look on this example. Okay, using the ideal diode equation just now that I have shown you. This example asks you to calculate for the ID, the current in PN junction diode, for two conditions. First, when the Vd is 0.7, and the second one when Vd is negative 0.7. Okay, what does it mean? For Vd positive 0.7, it means that at that time the PN junction is under forward bias. We give positive voltage to PN junction. Okay, so if we use the formula, substitute all the values, we are going to get ID is 4.93 milliampere. Okay, so because we are talking about forward bias, right, there will be diffusion of carriers. Obviously there will be current flow, so in this case the current is 4.93 milliampere. Okay, then for the second condition where Vd is negative 0.7, okay, which means the PN junction is under reverse bias. So if we substitute the values into the formula, you are going to get ID is very small, indicating actually there is no current flow, but it is understood under reverse bias, the depletion region is so wide, it will be difficult for the carriers to cross the junction. Obviously, there won't be any current. Here is another example, but you may do it on your own for your self-revision. Okay, talking about PN junction diode, okay, we have a symbol for this diode, which is given by this. This is the symbol of our PN junction diode. We have a triangle like that. Okay, then this side will be the positive terminal, and this side will be the negative terminal. Okay, remember the anode and cathode. Okay, the positive one is the anode, the negative one is the cathode. Okay, and another thing that you should take note that in diode, our PN junction diode, the current only flows in one direction. Current can only flow in one direction, from positive to negative. Remember the forward bias and reverse bias. Okay, so the current can only flow from positive to negative, indicating under forward bias condition. Then when it is in the opposite, current cannot flow. Okay, so you might see much better when we refer to this IV characteristic, ID versus VD. Okay, then when VD is positive at the positive region, actually here we are referring to forward bias region. Okay, then as you can see from this region, initially the current is still zero, although we are talking about having forward bias region where the depletion region becomes narrower, remember, where diffusion of carriers is possible. Okay, but initially there won't be any current flow. Why? Because at that time the voltage is still not enough to overcome the voltage built-in. Remember the built-in potential? Okay, the energy required for electrons to cross the junction. Okay, so at that time, although the voltage is positive, although it is forward bias, but at this time this voltage is still less than the built-in potential. Okay, so once the VBI is achieved, once the VBI value is achieved, in this case we can also call this situation as V gamma. Okay, the turn on voltage, then only there will be current. Okay, then only there will be current. Okay, then if you look at this negative side, where we are having negative voltage, okay, obviously here we are talking about reverse bias region. Okay, remember reverse bias region, depletion region becomes wider. It's possible for the carriers to cross the junction, so obviously here there is no current flow. Okay, so this is just the same explanation, but when we talk about the diode symbol, this is the symbol. Okay, this one is just the diode structure. It shows the p-type and n-type connected together. When we talk about symbol, you should show this one, anode and cathode, positive and negative. Okay, here is the same thing. Okay, the IV characteristic, ID versus VD for the PN junction diode. This one is more realistic because it shows the actual diode characteristic, meaning to say when you come to the lab, you take a diode, there is a data sheet, so you can get the data sheet and see this kind of curve on the data sheet. So it can tell you many things actually from here. Okay, where from here you can see that in reality, okay, if we talk about the ideal diode equation, okay, that we referred before, it follows this curve, but in reality actually the commercial one, the curve is at a little bit at higher voltage, okay, because of few reasons. Okay, but this is the actual diode characteristic. The curve pattern is about the same, it's just that the turn on voltage maybe for this commercial diode is much larger compared to the ideal case. Okay, we are coming to that later in next video. Okay, then another thing that I want to highlight, remember before this, for ideal case we are saying the current is zero, but actually in reality there will be some currents, but it's very small. Okay, so for the sake of simplicity, we can just ignore it. We can just say the current is zero because it's under reverse bias, but in reality if you come to the lab, you measure the current, actually there will be some current, but it's very small. Another thing that I need to highlight in related to this IV characteristics of PN junction diode is the temperature effect. Okay, it means that this diode characteristic actually may vary with temperature. Okay, meaning to say, if let's say, remember we are talking here about V gamma or VBI value, right? where we are saying that the carriers need to obtain certain voltage in order for them to cross the junction, to cross the depletion region, remember, right? Okay, in some cases, when the surrounding temperature is higher, or we give additional heat to the diode, okay, actually the VBI or V gamma value can be lowered, okay, because the carriers already receive some kind of energy coming from the heat or the temperature. Okay, so it means that it just need just a little bit more of voltage connected to the diode for them to be able to produce current. Okay, meaning to say, in this case, the higher the temperature, the lower will be the V gamma value. Why? Because the diode is getting energy also from the temperature. So if the temperature is higher, the diode is getting more energy from temperature. So because of that, less voltage is needed to turn on the diode so that the current can flow. Okay, I think that's all about chapter 2B, okay, where we talk about the currents in semiconductor as well as about the PN junction diode, okay. Then let's meet again in next video. Okay, before that, my message to you, let's amplify the goodness around us and rectify our mistakes through Islamic electronification of our lives. Okay, with that, thank you so much. Bye.